everybody. I'm glad so many people have arrived here, and I thank especially Luba for organizing this meeting, and Eric for helping him to keep on track. And I thank Uriel for giving us this opportunity to talk about turbulence and other aspects way beyond that topic. It's a great opportunity to welcome you at the new NODIDA. You remember NODIDA used to be in Copenhagen, and it was founded in '57, which is almost 55 years ago. And there's so many things, they don't live in the same way forever, they change, and so the type how NODIDA operates has changed, and it has changed its location. The reason why NODIDA was produced back then in '57 by Niels Bohr was that that was the time when CERN was established, and there was an attempt to have CERN actually in Copenhagen at the time. That obviously failed, and as a counterweight to that effort, Niels Bohr thought to have a corresponding theory center on atomic physics. And the A in the NODIDA at the end refers to atomic physics, not to astrophysics, as some people sometimes think. So it's the Nordic Institute for Theoretical Atomic Physics, I think it used to be called back then. And then later on, of course, the name changed, or at least the meaning of the name changed, and the name was preserved. So it was, in that sense, meant to be a counterweight to the efforts at CERN. But of course, again, this effort has changed a lot in the years. One of the big differences, or one of the big assets of the time when NODIDA was established, was that that was basically one of the few places where one could have postdoc places. At various institutes in those 50s, of course, individuals had every now and then some visitors and even postdocs, but the concept of postdocs, at least in Europe, was a relatively new idea. And so, of course, at NODIDA we had a fair number of postdocs already since the very beginning. So that was one of the big things why NODIDA was an interesting place for the neighboring countries, especially the Nordic countries. And so in that sense, NODIDA was founded or supported by the 5 Nordic countries. Again, many of these things have changed in the last few years, especially with the move of the institute here to Copenhagen. It's no longer the Nordic Council of Ministers which owns the institute, but it's a consortium consisting of Stockholm University, KTH, and Uppsala University. The professors, we have a permanent staff of 3 professors: astrophysics, condensed matter physics, high energy physics. They choose to have a permanent affiliation with one of these 3 universities. That's how it's being set up. I myself am here at Stockholm University at the observatory, astronomy department. We have Konstantin Zarembo, who is associated with Uppsala, and we will have Balatsky. We will have Balatsky coming in condensed matter physics, and he will be associated with KTH. But that's a random choice. It can be any other of the other different places. Also, NODIDA continues to have a staff of some 13 at the moment postdocs. Together with them, we have a lot of visitors, 6 visitors at the moment. We also have students. In addition to some of the students that are being hired on individual grants, we have short-term visiting studentships. These are mostly designed for people from the Nordic countries and gives them and us first exposure to the young people that might come up as a postdoc in just 1 or 2 years' time later. The overall budget of NODIDA is on the order of 24 million Swedish kronor per year. Half of that is being supplied by the Nordic Council of Ministers still. The other half is shared to 1/4 by the Swedish Research Council, Vetenskapsrådet, and the other half comes from the host universities. In this case, it's KTH and Stockholm University. So I think, we are proud, of course, if NODIDA is able to attract big signs of recognition. Of course, when I got my ERC grant, that was one of them. But the most recent addition is the so-called Tage Erlander guest professorship which is being awarded in Sweden or to foreign individuals to stay for 1 year in Sweden, and it's over very many different fields in natural sciences. And this year went to physics, and it went to John Wetlaufer, who got the Tage Erlander Fellowship for us this year. So I think not only John can be very proud, but also Nordic can be very proud to be able to host such a prominent fellowship here. So with these words, I'm already over time, but let me then give Dhruva the chance now to organize the rest of.
Okay, not really the rest because Eric takes over, but just welcome to everybody, and just two things. One is that so the preliminary program is actually only preliminary. So there is to look at the real program, you have to look at the link timetable. There are some talks which are somewhat reshuffled. Of course, I will inform the speakers that their talks have actually been reshuffled. So that's fine. And the second is that please don't forget to fill up the reimbursement forms and give them to Anne. If you have mailed them already, that's fine. If you have not, then please fill them and give them to Anne.
Okay. So as a representative of the locals, I should say also thanks to Rodita for moving here. It's been fantastic to have this larger community of people with our shared interest in Stockholm. And one thing that Axel brought is this wonderful conference software called Agenda, which though has this quirk that somehow things come in the wrong way. For instance, timetable is now the schedule, right? For some reason. So yeah, it's always been like that, and if you have to blame somebody, the ones who made the software are Axel. There are two things which Dhruva asked me to say to everybody except to welcome. So first is there is a conference dinner on Wednesday, correct?
Yes.
And that one is subsidized to 50% by Nordita, but you have to pay a ticket for the other 50%. I guess that goes for everybody except maybe Uriel. I'm not sure. Dhruva would know. But for the rest of us, it's so. Okay? So if you want to participate, you pay half. And you have to pay that ticket in advance. The other one is all the talks will be filmed. And I guess I am on tape right now. So if you have any objections to being filmed, or if you have any objections in the film of you being made public later, then you have to voice that concern to Dhruva or to us.
We can delete it.
Okay. And with this, I give the word to Rahul, who's the chairman of the first session, please.
Okay, welcome to the first session. We are slightly behind schedule, so speakers will help me by sticking to the half an hour. Half an hour for me means 25 minutes plus 5 minutes for questions. If we go beyond 25, then there'll be no questions. Okay.
Yes.
Guido is our first speaker, Guido Bocchetta. He'll talk about turbulent convection in 3, 2, and 1 dimension.
Thanks to the organizer for bringing me to this interesting conference. And what I will present today is some recent result. Some result were obtained not so recent, in the last couple of years, within a collaboration between Torino, Genoa with Andrea Mazzino and Nice, Stefano Musacchio, on relative of turbulence in 3, 2, and quasi 1D. So the general idea, the general motivation of our study is that we all know since the fundamental work of Kash in 1967 that changing the dimensionality in the turbulent flow can change dramatically statistics. When you go from 3D to 2 dimensions, you see an inversion of the flux, kinetic energy go to large scale instead of small scales. More recent work based on numerical simulation and some theoretical model showed that this transition is not sharp. It can occur, also in a thin layer. You don't need to go exactly to 2 dimensions. You can consider a 3-dimensional flow with large aspect ratio, so a thin layer of fluid, And in this case, you also observe an inversion of the flux, but this inversion is not sharp in the sense there is the inversion transition from three-dimensional, from a direct to the inverse cascade, is somehow a smooth function of the aspect ratio. So we wanted to investigate this effect of geometrical confinement in turbulent flow within the framework of turbulent convection. In particular, we use Rayleigh-Taylor turbulence, which is probably the simplest example of turbulent convection because of the absence of boundary layers. It's much simpler than Rayleigh-Benard, for example. And we want to impose this confinement not with a physical boundary. In order to keep homogeneity, we impose periodic boundary condition at a given scale, which is the confinement scale in the box. Okay? And I will discuss two results. The first one is what happens when you confine the system in one dimension, so a quasi-two-dimensional setup. And we will see the appearance of a new dynamical scale, the Boltzmann scale in the fluid. And then I will present some new result on the confinement in two dimensions, so quasi-1D Rayleigh-Taylor setup. So the equation of motion for Rayleigh-Taylor turbulence, I consider two layers of fluid, the same fluid, for example, at different temperatures, so different density, with a layer of cold water on the top of warm water, so you are gravitationally unstable. And the temperature charge across the interface defines the absolute number, and if this, which is essentially the relative density difference, and if the absolute number is small, you can assume that the Boussinesq approximation for incompressible fluid flow holds. So you get this equation, which are the standard Navier-Stokes equation, plus an additional term which couple the velocity field to the temperature field, which is transported by velocity. So this is the model we will use. And I will consider, this is not stationary turbulence, which evolves in time as a consequence of instability, and the initial condition is velocity is zero at the beginning, and we have an unstable jump of temperatures across the interface. So the phenomenology of Rayleigh-Taylor turbulence at large scale is very simple. You can obtain four-dimensional arguments. So what I show here is a short movie of the Rayleigh-Taylor turbulence. So this is the one section of the flow with represent the temperatures. So black is cold and white is hot, warm. And this is the interface. And then you see that there is the, okay, you see the development of the instability, then the instability eventually develops in a turbulent layer that grows in time in the domain. So from the energy balance, you can obtain a lot of information, because you have that in the system, in the turbulent flow, kinetic energy, time derivative kinetic energy is produced as the loss of potential energy plus viscous dissipation, minus viscous dissipation actually. It's so dimensional, you can regard the time derivative of u squared as proportional to this buoyancy term. Theta 0 is the temperature jump. And so immediately you get that large scale velocity fluctuation grows linearly in time in the system. As a consequence, a typical scale, for example, the width of the mixing layer, grows quadratically in time. Is not a surprise, it's just motion under constant acceleration. So it's very simple. What is less trivial in this result is that the kinetic energy in the turbulent mixing layer is pumped in the system at a rate which is not constant, but grows linearly in time. So we have a time evolving turbulence. So for what concerns the small-scale property of this turbulent flow, there is a paper by Michel Chertoff in 2003, which explained the dimensional analysis to small-scale statistics. So now we want to do something some dimensional analysis at a Kolmogorov scale by scale. So we have an equation which, with respect to use of Navier-Stokes, we have this additional term, which is the buoyancy term. So you have to make some ansatz. One possible ansatz is that the buoyancy term at small scale becomes negligible. Okay, this is just an ansatz you can make. So if you assume that this term, you can neglect this term at small scale, it means that at small scale you recover a standard Navier-Stokes equation plus a passive scalar. And so immediately you recover the standard Kolmogorov form of phenomenology with scaling exponent 1/3 both for velocity and temperature fluctuation. The only non-trivial part here is that there is a time dependency due to the fact that kinetic energy is injected linearly, goes linearly. The energy force. Okay, this is the prediction, and this prediction is at least consistent in the sense that if you now consider the ratio between these two terms, okay, these two terms in the cascade, you see that the buoyancy term becomes negligible at small scale in the direct cascade, both in space and in time. So it is a consistent prediction. And of course, this is not consistent in 2 dimensions, because in 2 dimensions you have the cascade goes to large scale, so it means that you have arc that becomes large. So in that case, that this assumption will be violated at a certain point. And so the prediction for 2 dimensions is different. It was already done by Chertot in the same paper. And the other possibility is that the buoyancy term is not negligible in the cascade, but inject the energy in the system at every scale. So you assume to have a scale-by-scale balance between these 2 terms, which we mentioned in this way. And so with these answers, you get a different prediction for the velocity and temperature fluctuation, which follow different scaling exponent, 3/5 for the velocity and 1/5 for the temperature fluctuation. And this is the well-known Bolzano scaling, which was introduced by Bolzano in the 50s for the statistics of turbulent stratified flow, okay, with a different temporal scale. Okay, these are the predictions for the 3-dimensional and 2-dimensional case, and these predictions are verified by numerical simulation. Again, here is another movie of our simulation. You see again the evolution of the temperature field, and measure by the temperature field, you can define the mean temperature profile, averaging the temperature of the horizontal plane, and this is the profile as it evolves in time. And then from this profile, you can define what is the width of the mixing layer that follows the quadratic law quite clearly. Okay, and for what concerns the small-scale statistics, just very briefly, just one slide, we show you the spectra of both velocity and temperature fluctuation. They are rescaled here with the dimensional prediction. Okay, and you see there is a short range of scale in which the Kolmogorov-Overton spectrum is observed, more or less. And the evolution is similar, because if you rescale with the dimensional prediction, which is here for the spectra, you find a collapse in the inertial range of scale. Okay, so the numerical simulation are in agreement with the dimensional theory I showed before, and also for the 2-dimensional Rayleigh-Taylor turbulence, there has been simulation by Celani, Mazzina, Bozzella a few years ago, and also in that case they observe a Bolzano scale as predicted. This is the velocity structure function of order 2, 4, and 6, and these are the prediction of Bolzano scaling, the blue line. Where for temperature field, they observe some intermittency correction for higher order structure function, but nevertheless a second order structure function is an agreement with Bolzano scale. So the situation is very clear, and now I enjoy the new part of our work. So the first question is, where is the Bolzano scale in this setup? So the Bolzano scale is the scale which was introduced by Bolzano, is the scale at which you have a balance between buoyancy and inertia. Okay? So in 3D, we have seen that buoyancy in the cascade is always subliving with respect to the inertial term, which means that the Bolzano scale is the largest scale in the system. Okay? While in the inverse cascade, we have seen there is a balance between the 2 terms at each scale, so it means that the Bolzano scale is the smallest scale in the system. So our idea, which is very simple at the end, is that the Bolzano scale in this setup is determined by the smallest size in the box. So if we consider a box with the large aspect ratio, with one dimension much smaller than the other 2, and y for example, we can think that this transverse direction, the confinement scale, becomes the Bolzano scale in the flow. And so we expect to observe both Kolmogorov phenomenology at smaller scale and Bolzano phenomenology at larger scale. So to check this idea, we did a very high resolution numerical simulation together with Stefano Musacchio, and the simulation is, as this aspect ratio I showed here in the picture, is 4,000 times 3,000 times 128. And okay, this is a two snapshot of the temperature field. Is not very, okay, I can skip. So the first signature of the transition from 3-dimensional to 2-dimensional phenomenology is you can obtain from the energy balance. Because in 3D, we have a direct cascade of energy. So it means that the energy viscous dissipation is proportional to the input, and they both grow linear in time as the time derivative of the energy. So it means the ratio between two quantities is constant. Okay? While in 2D, when you have a crossover to 2-dimensional phenomenology, you have an inversion of the flux, so viscous dissipation goes to 0. And so you expect that this quantity becomes small, but you have a residual flux in two dimensions in the transition because you have a matching of the scaling the velocity at the confining scale. So matching the two scaling behavior, you get a prediction for the decay of the viscous dissipation after the transition. And so you have a prediction that the time derivative of kinetic energy over viscous dissipation of energy, you're like t to the power a, okay, this to the power 8/5. Okay, this is indeed what is observed in our simulation. So after the transient, we have developed turbulence here, which is at the beginning is three-dimensional because the scale is smaller than the confinement scale, so everything is like three-dimensional. And so the ratio between the kinetic energy derivative and viscous dissipation is constant, is roughly 1. And then when the scale becomes larger than the confinement scale, you have a transition to two-dimensional motion. There is an inversion of the flux, and you see that this ratio go like, okay, we have very large fluctuation because it's large scale is a large scale quantity, so we have only varialization, but nevertheless, it's compatible at least with this.
It doesn't seem like fluctuation, it seems like an oscillation.
There are some oscillation due to the fact that you have very big plumes here. Okay. Yeah, this is only one realization of the flow. It is a large scale quantity, so it's affected by fluctuation. Yes. Right. For small scale quantities, it will be much better. We show you what I say. So what you expect is that at a certain point, so there is an inversion of the flux, and after this point, you expect to have a double cascade of energy. I mean, not a usual double cascade in 2D. Some of the energy goes to small scale in the double cascade with a vanishing flux, and some of the energy goes to larger scale. So, and indeed, if you look at the flux, the energy flux, which is, for example, the third order structure function, velocity structure function, you see there is indeed a change in the sign. What I plot here is minus S3, which is the blue point, and plus S3, the red point. And you see that indeed at the scale comparable to the confinement scale, the S3, the flux change sign. The flux is negative for small scale, which is compatible, at least compatible with Kolmogorov for fifth law. Okay, we don't see any scaling here because the range of scale is very small. And then after at larger scale, the change sign become positive, so inverse cascade with an exponent which is at least compatible with the Boltzmann. Okay? The scaling exponents are very, you cannot see any scaling here because the resolution is not small, is quite small for both the two separately, and also because it changed sign. But if you look to second order structure function, for example, you will see much better scaling. So this is second order structure function for velocity from temperature fluctuation, okay, at the same time. And here you see quite clearly, we say the Kolmogorov scaling are small scale and Boltzmann scaling are larger scale, both for velocity and temperature fluctuation. Okay.
Can you remind us, is there any exact result for S3 in the inverse regime?
For this one, no.
Why not?
There
should be in principle, no? Because S3 has a simple...
you have the input by the temperature, it's not only for velocity.
Ah.
You have the temperature pump and the energy the system edge scale, so at least you have to
couple.
I will say not, but I'm not sure. I'm not sure about that.
It's interesting.
Yeah. It's not constant flux. Okay. In any case, the important result here, what I think is a nice result, is the clear first numerical evidence of the Boltzmann scale in the sense of two different scaling in numerical simulation of thermal combination. Okay, this was the first result I want to show you, and then I move to the last part of my talk about quasi-one-dimensional turbulence. And so now we want to impose two confinement scales, two confinement lengths. So both Lx and Ly are much smaller than the direction along the gravitational field. This study was also motivated by some experimental study on mixing efficiency in stratified fluids done experimentally by the group of Dazer in Cambridge. And what they do exactly this experiment. They put some water with different densities, so salty water and fresh water. They turn around the setup. What they see is this is some picture taken from their experiment at different time. It is a very long pipe. The picture is taken at time from 0 to 140 seconds. And they put some dye in the salty water, so you see how the two fluid mixes in time. Okay? The output matter is very small, quite small, so it's reasonable to use using this approximation. And what I show here is the same picture taken from our simulation. So these are sections of the temperature density of fire density field taken at different time with equal time step between one and the other. And so already from this picture you see something which is interesting, that the growth of the width of the mixing layer, okay, in time is not quadratic anymore. You see. Okay, it was quadratic in both in 3 dimension and 2 dimension, and here is something different.
Square root.
It's not square root. Close to square root, but not square root. This is the interesting point. Okay, so this is the width of the growth of the mixing layer as a function of time. So you have a transient at the beginning it's exponential because it's the linear stage, then you enter in 3-dimensional. Okay, the flow is 3-dimensional. Right? We have also resolution of the application, so a 3-dimensional flow. You enter a 3-dimensional regime with this square, and then you see a crossover to something different. And I want to discuss what is this law. And the interesting point is that this transition happens when the scale of the mixing length becomes comparable with the confinement scale. And what we discovered that, sorry, to do on the other side. So we discovered the transition corresponds to the fact that the velocity correlation scale, this is the velocity correlation scale taken by autocorrelation, the velocity saturates. This is the velocity correlation scale as a function of the width of the mixing layer. At the beginning, you don't see here because this is a linear plot, but at the beginning they are proportional, one to the other. And then you see a saturation scale. So if you have a saturation or correlation scale, it means that the velocity fluctuation at the 2 points which are very far in the sense of mt are essentially uncorrelated. So you can assume that you can think that to use a very simple model like the diffusive model to estimate what is the growth of the mixing layer in this setup. So we write that the H is the width of the mixing layer with an eddy diffusivity, and we want to model the eddy diffusivity in terms of typical velocity fluctuation and typical scale. Okay, the velocity fluctuation you can get dimensionally from balancing the equation, the buoyancy term with the inertial term. Okay, this is what we get. And now we have two situations. So this is the idea. At short time, when the mixing layer, the width of the mixing layer is smaller or for the order of the confinement scale, you have that, what means? It means that the large scale head is smaller than the confinement scale. So it means that it is proportional to the width of the mixing layer, and the temperature jump, which drives the velocity fluctuation across this eddy, is of the order of the total temperature jump. Okay, so theta L is equal to theta 0, which is the constant temperature jump. You put in the definition, and you get for the eddy diffusivity this expression that gives you the T-square law. Okay, this is standard dimension. Then at a later time, the idea is that the large scale eddy cannot grow more than the Traveler scale. Okay, it's fixed at the Traveler scale, and so it becomes constant. On the contrary, the temperature jump across the scale is not the total temperature jump in the flow, but is reduced by a factor, geometrical factor given by this expression. Okay, if you assume to have a constant linear profile, very simple. So you use these two increments, and you get for the eddy diffusivity something which decreases as h to 1/2 to -1/2, and you end with a prediction that the growth of the mixing layer is not diffusive, but close to this 0.4 exponent. Okay? Because it's diffusion with an eddy diffusivity with decays in time. It's very simple. Okay, that is not. Okay, one consequence before looking at this, showing this picture, another consequence of the prediction is that the velocity square, so kinetic energy, is inversely proportional to the width of the mixing layer. So it means that the integral of total kinetic energy, if you take the integral over all domain, you have a u squared times h, this becomes a constant. And indeed, in our simulation, we find that at late time, the total kinetic energy is more or less constant, with some fluctuation, and you will see in a trend more. And now, because we think that this model works pretty well, we can extend the model to a local model for the diffusivity. So we want to write an eddy diffusivity model for the mean temperature profile in the usual term. So now what is the difference that we want to have a local evaluation of the eddy diffusivity, The only difference with the previous argument that I showed you is that now the temperature jump use a local estimation of temperature jump in terms of the gradient of temperature profile. It's very simple. It's an argument about current mixing. So if you impose this, if you assume this estimation, you end with this nonlinear diffusion model for the mean temperature profile, for which you can get very simple solution. If you look at for solution, it's a similar solution in this form. And you get a prediction for the mean temperature profile in terms of a polynomial of order 5. Okay, it's not very important what is the actual prediction. The important thing is now you have one parameter, theta 1, which represents the width mixing layer, which you can fit for the actual profile for numerical simulation. And because you have a form for this profile, the fit is very accurate. This is the deal here. You can use this model to have an accurate fit of the mixing layer. And indeed, these are the pictures. So what I got here is the mean temperature profile. Now it's called T instead of T, so that is the same. At different time, they are rescaled with theta 1 that you estimate from the fit. And this is the theoretical model. It works, of course, works pretty well. And from different fit, you get different evolution. Theta 1 is a function of time. That is the final result. We have the evolution of theta 1 as a function of time. You can try to compensate with exponent 0.4, and you see a perfect compensation. Okay, so it's a significant evolution of the mixing layer. In order to get you an idea of the quality of the statistics, if you try to compensate, for example, with diffusion, 0.5, you see there is a deviation. Okay, so I think this result is correct here. And so this is the end of my talk. That's all I wanted to show you. This is without conclusion, but if you're interested more in details on what I presented, you can find the paper on my webpage. So thank you very much for your attention.
We kindly left some time for questions. We have time for questions while Eric closes his talk.
I mean, the issue of dimensionality here is rather distinct from my concept of changing from 2 to 3 dimensions, where at least in the RG sense I could talk about an critical dimension. Here it's just where you impose periodicity. And so it seemed to come out in the last example where you have 1 dimension and you compare to the DL, or you're motivated by the DL et al. Experiment, which has really got boundary conditions.
Yeah.
So do you want to comment about that?
Yeah, okay, there are 2 questions probably, at least your comment. About the last question, of course, boundary conditions are very different from our theory boundary condition, but at the level of this, the evolution of global quantity doesn't matter so much, because the experiment, they say, they observe the same scaling of the same exponent. They claim, okay, the experiments are less clear than the simulation, but doesn't change too much. Probably the numerical factor will be different, but the scaling will be the same. Okay? But the mechanism is what is about. The fact that you cannot have, you have some kind of diffusivity decays in time. For what concerns your first question, of course, one dimension in incompressible flow doesn't exist, so we have to have a quasi-1D setup. I think it would be very interesting to see if there is some symmetry of one dimension in velocity fluctuations. So no one the statistics, but the statistics must be larger than a confounding scale, but we don't have the result.
You had, in all your plots, you had a plot of T over tau, so this is low level. What was that tau in your plots?
In 3D?
In any D, what is the difference?
Yes, it's a characteristic time in the flow. For example, is the time it takes for a free flowing object with the same density to go across the place. It's a characteristic time because that's the very scale of the time. Okay. So gravity and temperature.
Right. Yes, question?
You know, in the Marjana scaling I was asking about, so you know, in OHD, balancing nonlinear and linear term, people call critical balance. So, I mean, do you think there is any, and well, of course, one has to motivate this kind of balancing. So, what would be here, physical reason for Bolzano scaling in 2D and not 3D? Some sort of wave breaking?
Bolzano scaling was proposed originally for stratified 3D, stable stratified 3D as far as I know. But indeed, what I don't know why, but my impression is that Bolzano scale works in 2D because of the balance of buoyancy and inertial term. You have that energy is pumped in the system at all scale. So you not constant flux cascade. Okay? But in a direct cascade, if you have a flux which is not constant, it becomes less steep than from the floor, which is not what Bolzano predicted. While in an inverse cascade, if you pump energy in the system at all scale, there's something which is more steep, which is very to large scale, which is compatible with Bolzano. This is the only idea I have why you serve Bolzano to be not in it's not deep, but no other argument.
Isn't it just the size of the Bolzano scale? Because in 3D, the Bolzano scale usually is very, very large, larger than the boxes.
It's the boxes, yes.
But if you had a large enough box, you see it also in 3D. I mean, it's just the size of the Bolzano scale that you have here. Pin the situation where the Bolzano scale is small enough so that you can see it.
Any other questions? If not, wer kommt klein wieder?